Welcome, everyone. Today, we are diving deep into the world of machine learning operations, commonly known as MLOps. If you have ever wondered how to take a machine learning model from a data scientist's experimental notebook and reliably scale it into a secure, production-ready environment, you are in exactly the right place. We will explore the entire lifecycle from training and tracking to automation and deployment. Let's get started. Let's begin by defining MLOps. Think of MLOps as the intersection where machine learning meets traditional DevOps. In the past, a data scientist might build a brilliant model on their laptop, but getting that model to work reliably in a live application was a nightmare. That is where MLOps comes in. It covers the entire workflow: your data pipelines, model training, and eventual deployment. Why do we need this? Because machine learning models are not static. They degrade over time as real-world data drifts. MLOps provides the automation and source control required to rapidly update and deploy models without breaking your production systems. By the end of this training, you will understand how to transition from manual experimentation to a systematic, automated engineering discipline. Take a look at this diagram. It illustrates the core concept of MLOps. On the top left, we have traditional machine learning, and on the top right, DevOps practices. When we merge these two disciplines, we create the MLOps engine in the center. This engine then drives three continuous loops: continuous integration for packaging code and models, continuous deployment for safely releasing those models, and continuous monitoring to ensure the model performs well in the real world. Now, let's explore the MLOps solution architecture. To scale machine learning effectively, we need a robust, future-proof blueprint. We break this down into several key phases. First, we have the inner loop, which represents model development. This is where your data science team explores data, trains, and evaluates the model. Once a model is ready, we move to continuous integration, packaging, and registering that model. Then comes the outer loop, which handles model deployment and continuous deployment, testing the model in a staging environment before promoting it to production. Finally, we establish continuous monitoring to trigger retraining when needed. By separating these loops into distinct environments, like development, staging, and production, we ensure that experimentation never accidentally disrupts your live, customer-facing applications. This flowchart represents the journey of a model. On the left, in the inner loop, data scientists prepare data, train, and evaluate. Once successful, the model crosses into the CI/CD phase, where it is packaged, registered, and pushed to a staging environment. Finally, in the outer loop on the right, the model reaches the production endpoint. Notice the feedback loop at the bottom. If our monitoring detects a performance drop, it automatically triggers a new training cycle back in the inner loop. Let's zoom in on the inner loop: model development and experimentation. When you are tasked with building a model, you rarely know upfront which algorithm will yield the best results. We solve this using two complementary approaches. First, we use automated machine learning, or AutoML. Think of AutoML as a massive parallel search engine. It automatically applies data guardrails, scales features, and tests dozens of algorithms simultaneously to find a strong baseline. But AutoML is just the starting point. For deep, specialized tuning, data scientists transition to interactive notebooks. Here, they can write custom training scripts, engineer highly specific features, and push the model's performance to its absolute limits. It is the perfect balance between automated speed and manual precision. In this diagram, we see how raw data is converted into an MLTable data asset, which feeds into our experimentation phase. You have a choice: take the top path through AutoML for a broad, automated search that yields a strong baseline model, or take the bottom path using Jupyter Notebooks for manual, fine-grained control to create a custom-tuned model. As you iterate rapidly in your notebooks, you run into a critical problem: keeping track of your experiments. If you train 50 models in a week, how do you remember which hyperparameter combination produced the best accuracy? This is where MLflow becomes invaluable. MLflow is an open-source tracking library that integrates seamlessly into your MLOps pipeline. With a single line of code, like mlflow.autolog, you can instruct the system to automatically record your model's parameters, performance metrics, and artifacts. You can easily compare dozens of notebook runs side by side. For highly specialized metrics, you can use custom logging functions to record exact data points or even generated charts. This guarantees absolute reproducibility and auditability for every experiment you run. This diagram breaks down the MLflow tracking process. As your training script executes, the MFlow tracking engine captures the data. It splits this data into 3 streams: parameters, like your learning rate; metrics, like accuracy or loss; and artifacts, the actual model files or charts. All of these streams are centrally stored in the machine learning workspace for easy comparison. Once you have a working script, it is time to squeeze out every drop of performance through hyperparameter tuning. Hyperparameters are the configuration dials of your algorithm, like learning rate or batch size, that you must set before training begins. To find the perfect combination, we use a sweep job. A sweep job initiates multiple trial runs, sampling different configurations from a search space using grid, random, or Bayesian methods. However, training dozens of models can be expensive and time-consuming. That is why we use an early termination policy, such as the bandit policy. If a trial is performing significantly worse than our best-known model, the system terminates it early, saving you compute time and money while still discovering the ultimate model configuration. Here we see the architecture of a sweep job. We start by defining a search space and a sampling method, which initiates multiple trials, concurrently shown here as trials 1, 2, and 3. Each trial's performance is constantly evaluated by the early termination policy. If a trial is underperforming, it is killed instantly. If it is performing well, it runs to completion, and the best model is logged. Automation is the beating heart of MLOps. To automate our workflow securely, we rely on GitHub Actions paired with feature-based development. Here is the golden rule: absolutely no one pushes code directly to the main production branch. Instead, data scientists experiment in isolated feature branches. When they are ready to update the model, they open a pull request. This pull request automatically triggers a GitHub Actions workflow defined in a YAML file. This workflow securely connects to Azure using credentials stored in GitHub Secrets, and it automatically runs your code quality checks and ML training scripts. This ensures that every single piece of code is validated in the cloud before it ever merges into your main codebase. This flow shows the automation lifecycle. A developer works in a feature branch and opens a pull request. This triggers GitHub Actions, which securely authenticates using stored secrets and runs the training pipeline. If the model passes our automated quality checks, the PR can be merged into the main branch. If it fails, the PR is rejected, keeping our production code pristine. Training a great model is only half the battle. We must deploy it to generate value. In the outer loop, we package the model and register it. Because we tracked it using MFlow, we can take advantage of no-code deployment, meaning the system automatically generates the scoring script and environment for us. We deploy the model to an endpoint, either a real-time online endpoint or a batch endpoint. But we don't just push to production blindly. We push to a staging environment first. Here, we use environment gates in GitHub Actions. A required reviewer, a human in the loop, must manually inspect the staging tests. Only after they approve the results is the model deployed to the live production environment. This diagram tracks the deployment strategy. Our registered model is first deployed to a staging environment where automated tests run. Crucially, the flow pauses at a manual approval gate. A lead engineer must review the results. If approved, the deployment proceeds to production, exposing a real-time endpoint. If rejected, it loops back to the development team. Let's bring all these concepts together with a real-world use case. Imagine a healthcare startup named Prosware. They have built a web application for medical practitioners, and they want to integrate a classification model that predicts a patient's probability of having diabetes. This acts as a critical first filter to prevent unnecessary, costly medical tests. Using our MLOps framework, Prosware's data scientists experiment in secure dev environments. When they update the algorithm, a pull request triggers GitHub Actions to automatically retrain the model and test it in staging. Upon approval, it deploys to a real-time online endpoint. The web app pings this endpoint instantly during patient visits. Best of all, as the model learns from new regional data over time, Prosware can update the backend model seamlessly without ever changing the web app's architecture. In this final diagram, we see the live production flow at Prosware. A doctor enters patient data into the web application, which sends a secure HTTPS request to our online endpoint. The endpoint passes the data to the diabetes classification model, which instantly generates a prediction score. This score flows right back to the web application, allowing the doctor to view the risk assessment in real time.